Hello everyone and thank you for joining. I'm Chen and I'm honored and excited to be here today at DEF CON 29 and share our research about exploiting cross-document messaging. A little bit about me. I'm the co-founder and chief architect of Enzo Security. I live in Tel Aviv. I like to build things and hacking has been my profession since 2004. In this talk, I'm going to talk about what cross-document messaging is, how to hack it, and how to use it safely. But when we looked into this issue, to this subject, and tried to map what's the risks in it and how to handle it from an application security perspective, we found that when we are used to having very good tools in introspecting web traffic, in looking at the browser generally and being able to understand what's going on inside it, especially in places where our application interface with other applications, and from the perspective of a pen tester, this is a really interesting place. Cross-document messaging offers communication between different origins, different parties, practically, but there is little to no tools to actually properly look into these messaging protocols and understand what's going on inside them. So we decided to build our own tool, and therefore this talk is also about the tool and how and the research that we made in order to build it, and I hope you like it. So what is cross-document messaging? Cross-document messaging is window-to-window communication method that allows frames from different origins to communicate with each other. There is no network. Everything happens in the browser's memory. It's actually binding functions. Everything is already loaded in the runtime, and there is actually no network stack involved at all in these calls. And the security model that supports this is very straightforward and simple. Let's talk about the functional flow of cross messaging for a moment. So inside the browsing window, and the content, the document that opens inside the browsing window arrives from a specific origin. And this document may include script. This is basically some sort of a perspective on how every web page loads. There is an object called window that is managed by the browser and offers the API that documents and other elements in the runtime environment of the browser requires. And this window is what hosts practically the document and the script. Any document can open a new window and embed another document from another origin, or open a window using a window opener and open another window in another tab, and maintain a handle to that window so it can communicate with it later on. The scripts that run inside Windows, if they have reference to other windows, they can send messages to these windows using the PostMessage command. And they can also handle incoming messages by registering a listener on the message event on the window. This is practically allowing duplex communication between two different origins, say one page loaded from hacker.com and another page loaded from victim.com. They can still communicate with this technology, as long as they have reference to each other's windows. And in today, modern web pages and applications, there are always some use of framing, there's some use of reloading and referring another window, maybe sometimes in SSO scenarios, sometimes in just embedment. It's very common in sites that needs to tap and interact with ad networks. So the final result is that many web pages are very complex in the way that they build a tree hierarchy of windows. And because the way this feature is implemented inside the browser, because the way cross-document messaging is implemented inside the browser, every window in the DOM hierarchy can practically send messages to any other window or receive messages from any other window. This brings us to the security model, because In fact, there is no way for the developer of a specific document to know if it's going to be loaded in different environments. Everybody can try and load them as iframe, for example. And if they are implementing some interface, they're using some PostMessages capabilities, they are exposed to some different attacks. So the security model is very straightforward and simple. We have in the center in about how to start the session some security headers and configuration allow you to prevent the window or instruct the browser to not load this document in some scenarios. So for example, very known X-frame options will tell the browser to not load the document into an embedded window inside another window when even if the iframe points to your target window. Other security headers also restrict the use of a window opener. But as we all know about security headers, sometimes it's not very simple to be able to configure them. Sometimes the environments are very complex, and sometimes developers can override them. So security headers are one part of this model, but it's not, in many cases, sufficient to cover everything. So also on the code level, the sender code is responsible, and actually the browser forces, the API of the browser forces the sender to specify the remote origin, but it allows to specify any origin because in some scenarios you need to still send when you don't know who the recipient is, and in this case you're supposed to send only stuff that is not sensitive. On the receiving end, the browser provides authoritative information about the origin of the request, and all that is required from the side of developers is to verify that this origin is an origin that they trust, and then follow up, and only then process the request. So this is basically an outlook of cross-document messaging that explains the playground of security in this when this technology is in use. And I want to take it to a perspective of offense and defense to see how should we approach it from both directions, so we can actually understand what kind of tooling is the most appropriate and what kind of method is the most appropriate for testing and fixing PostMessages problem. So on the side of defense, we need to use security headers. We need to only send messages to selective targets, so don't just publish sensitive data to everybody. And we need to authenticate incoming messages. So defense is quite straightforward. We need to use security headers when we can. We need to instruct developers to only send messages to selective targets. If they are sending to wildcard, it must be something that is purely non-sensitive, if such a thing exists. And they need to authenticate incoming messages before they process them. Let's do a quick Stride drill down. So split it into two different scenarios. The first scenario is that our code is issuing a message, is using PostMessage, and then the risk is that the window on the other side is not coming from the origin that we think it's coming from, and the threats is the actual threat is information leakage, that we will send sensitive data to somewhere that we're not supposed to send it to. On the add event listener side, when our code is handling incoming traffic, so again there is a threat that the sender identity is not is spoofed, the sender is not who we think they are. And the threat of elevation is that the functions that the message instruct a function in our context, and that in this context, the instruction can give the attacker more privileges on doing some things, triggering some forward functions. We consider this as elevation because the attacker is elevating from running on a remote context into running in our context. Our controls for threats of spoofing the recipient identity is to not send sensitive to wildcard. and our control for making sure that we're not processing unwanted messages is to authenticate the origin of all messages and only allow messages that we trust and that we have controlled the contract with. Additional mitigation is to set up everything in security headers to restrict as much as possible the loading of our origin into other windows. So attack is also in two scenarios. The first one is to attack senders and listen to the data that they send to see if they send anything sensitive. And the second is to attack receivers by sending them messages and trying to run things in the remote context. We are addressing a few different weaknesses here. And the first weakness is that in some cases, even if Xframe option, for example, works, still you can use a window opener. And in some cases, it's very difficult to propagate the security headers everywhere that is needed to make sure that the window actually won't load in any risky scenario. As testers, we have to look at this and spot those places. We need to try and host the vulnerable frame and make sure that we host it in a way that is similar to a real scenario to actually make sure that it won't. And in most cases, it will be still possible either to operate in an window opener, or in an iframe, or maybe find another frame that has similar problems when you explore your target test scope. Second weakness is that in some cases, developer might be under the assumption that they are protected and send unrestrictedly to wildcard. We need to spot these places and see if any sensitive data is sent to any origin. This could happen because the developers think that they're protected, but it can also happen because they operate in a very complex environment where they need to work with many origins, and it's not possible for them to actually know which origin loads them. But still, sending sensitive data to unknown origin is dangerous, and this is one of the things that we need to track in our attack campaigns. The third weakness is that in some cases, developer will either skip the authorization check completely, or maybe implement some string matching that is inadequate to actually test if the remote origin is trusted or not. And in addition to that, we'll do something sensitive with the data that they receive. These are the three weaknesses we are addressing in two different attack scenarios. One is to spot chatty victims and listen to their traffic and report it back to our headquarters. And the second is to try and send messages to victims that implement sensitive message handlers. In this imaginary example, the victim on the other side will use this on-click URL parameter to update the source of the href of an A tag, and then instead of updating the actual link, it will load our JavaScript, and when a user clicks on it, it will actually load this JavaScript into the victim's browser. So let's get into working on our tool. So the first thing that we need to do is need to be able to see senders and their messages and receiver and their messages. Additionally, it needs to be able to simulate malicious senders or receivers, so we can actually check if the window setting allows us to actually implement a real exploit in real life scenario. So we split the work on the tool to a few different milestones. In this talk, we're talking about the two first steps, which is being able to see the tree of all windows in the browser, the listeners, the messages, practically the traffic, and be able to simulate different attack scenarios to see if we actually found a vulnerable listener or sender. Now we get into the research part. So this technology, the cross-document messaging technology, is really almost invisible inside the browser as it is. The straightforward way to see this communication is to open DevTools, go and look into a window object and look into its event listeners, and then follow to the message event listeners. But this is impractical when we talk about a lot of different test cases with a lot of different windows. It's almost impossible to accomplish this in large scale. You have to somehow automate this. So first thing we tried is to inject a JavaScript inside every browser session, every document to be precise, and have this JavaScript hook some calls inside the browser to make sure that some of the traffic flows through it, and using this method to be able to see all the traffic and the frames. The problem running this userland mode is that we didn't get enough data to show everything that we needed. And the setup was also unstable and complicated with additional extra steps to configure your proxy and make sure that it also handles all the content security policy restrictions that won't come into effect in a real world scenario because of how cross-document messaging works. So we tried to an approach that gives us a little bit more insight into the internals of the browser. First attempt was to use Chrome debugger with a Chrome DevTools protocol, connect to it from remotely, and operate the debugger API, different kind of APIs to collect and track the data that we need. This was very disappointed to find that this wasn't very accomplishable in this method. The debugger API, if you move into debugger mode, it affects the user experience. It breaks many things on some website in some cases, and it also didn't give us the data that we needed. And there is problems in the way that different frames are represented in different APIs, which makes it tremendously difficult to analyze this graph or this tree of frames loading. And then in the third approach, we benefit from extra additional options is by using an extension. It also properly accommodates our need for some UI. And the data, and it was a bit more simplistic, and the data that is in it was better, still not perfect, but better for us to be able to construct all the data together and show it in the way that you can actually see all the frames together. The final approach was a combination of different methods together to actually be able to do what we needed to do. Let me share the overall conclusion from this research. So the bottom line is that the browser does not provide an easy interface. Right? You can see web traffic and you have many tools to manipulate it and to inspect elements and to see all the data. There is no good interface, not for people and not for code, to look at this data. In different APIs of the browser, frames are represented differently with different IDs and different meaning to the ID. There is no clear way of you sometimes have to assume things. If you run in userland, origin level isolation limits what you see, and then you need to find a way to work with this. And the same goes for extension context aggregation. Is also an obstacle in some cases because the kind of impact, the kind of feature that we are looking for in our tool is to be able to see things in all contexts, because we want to be able to see all this traffic and manipulate it. So with these lessons from our research, we were finally ready to think about our tools components. The first component is the extension content page. Its job is to run first, basically. We wanted to use it in order to load the agent, but we couldn't do it directly from the extension content page because it is isolated from the document context. And we wanted the agent to run in the document context, but the extension, the way content page works, isolates it from the document. The agent itself implements a sort of a hub that hooks add event listener call, and basically wrap every call to add event listener in a way that we will see the message first and only then dispatch it to the actual event listener. And this is also why we couldn't run it in the content page, because the content page does not see the calls to add event listener from the document. It is isolated. Its context is isolated. The agent script is basically injected as a script by the content page to every new document that loads inside the browser. Then the extension option page is our UI. It's a React-based user interface for everything that we need in this tool. The extension background page is the backend hub, and everything that the agent sees is reported to the background page, and the background page also exposes the data object that the option page needs. And in addition to that, we have the test site and a small app factory that hot build all these components, so you could actually develop this without losing your sanity. So without further ado, this is Posta. We have a place here to see all tabs and the windows, place to see all the messages and listeners, the control panel to use some actions, and some text editor playground. Let's open our testing page. So this is the test page. It hosts at the moment a vulnerable iframe. Here we can see this is GitHub, this is not us, and this is our test page and the hosted iframe. Now let's take a look. Let's send something. Test. As we can see, what this iframe does is to add a text here to the iframe itself. Let's take a look in Posta. We can see this message. Let's resend it. Resend as string. And go back to the testing page. As we can see that the payload is actually being sent. Let's try something else now. And let's send as string again. Send, and we see another one. And this is how it works. You can also use the exploit page. So if you go back to Posta, you can open it in an exploit page, which actually simulates hosting this. And let's send this message again. This is not complete somehow. Send a string. But as we can see here, nothing happens. Let's try to see what the problem is. And the problem is that the different origin subframe try to create a JavaScript dialog. So it's basically browser blocking the alert box. And this is exactly why for these kind of scenarios, and also to test for window loading, we have the option to open as tab. Got it. And this is it. Let's try again to send a string, and it's here, and it works. So this is Posta. You can go to Benzo.io, or it will lead you to Benzo.io open source collection tool. Posta is the first one. Please feel free to take a look, download, and use in your tests. So of course, one of the first things we did is to put this tool into use in finding real bugs, like this one by Enzo CTO Barak-Tawili, which shows that there is an iframe, a specific iframe at the CDN of AliExpress, the CDN that is used by AliExpress, that when sent a specific payload would actually take this data and let it affect the main menu of the shop, By sending a specific payload, we manage to override the content of the menu and inject our own script that respond to interaction with the menu with executing this notorious payload. Let's wrap this up. So cross-document messages weaknesses are that by default, Windows can send data to each other. We need to add security headers to prevent this, to prevent our Windows from loading in dangerous scenarios. On the receiver script, there is no default authorization checks. Developers must implement code to do this. And the sender script can publish data without restrictively choosing who is going to get it. And again, we need to make sure that the developers won't send sensitive data to other origins. And we need to, of course, to always, like in every technology, and especially in technology that interacts with other parties, we need to make sure that we spot all implementations of this technology and test them. Some conclusions for engineers. So we implement security headers to protect your Windows. Make sure that you invest in this. This is an efficient and effective way. Only send data to explicit targets if you can, also something very important. And when handling messages, you have to look into event origin and make sure that it is an origin that you trust. A couple of words about Enzo. Enzo is an application security posture management platform. It allows AppSec teams to scale their AppSec activity to actually eliminate the chaos and lead their organizations to maturity with an autonomous discovery engine that finds out what assets you have and onboard them to your security tools. It gives you measurable, actionable information about the performance of your different activities and let you control all of it in a single pane of glass with a lot of tools to simplify and your day-to-day work as AppSec. Also, check out the appsecmap.com, our new open initiative to map vendors and solutions in AppSec, so vendors and practitioners can easily find each other and understand what kind of solutions are available for them in their AppSec programs. Thank you very much for listening. I hope you enjoy it. Enjoy the rest of the conference and see you next time.